This is Geometry, Lesson 8-5, Trigonometry and Area. In this lesson, we will be finding the area of a bunch of different types of polygons. For example, this shape right here, I'm going to try to find its area, and you can see our two examples. We're trying to find the area of the following polygons. This is very heavily dependent on a formula that we're going to be deriving in the first half of the lesson. Once we have that formula, it's going to be really easy to use using a calculator. Memorizing the formula is the hard part of this lesson. So to start with, let's find the area of this shape. I'm going to purely use numbers, and at the very end, we will generalize using variables. So first, let's count the number of sides. I have 1, 2, 3, 4, 5, 6, 7 sides. That means that this is a septagon. And I'm going to change this length so we don't accidentally confuse the side length for the number of sides. Let's call this length 9. So the general strategy behind every single one of these is to divide each of the polygons into triangles, the most basic shape. So I've already taken the liberty of dividing it into 7 different triangles. Our strategy is to find the area of one triangle, and once we find that area, we can multiply that by 7 to find the area of the rest of the triangles and adding them up. So how do we find the area of this one triangle? I drew it over here on the bottom left so we can analyze it a little bit further. Our first step is to figure out what this inner angle theta is. This inner angle theta right here comes from the fact that there is a 360-degree rotation to get through this entire inner rotation, and the fact that we have 7 of these angles. Each of these angles is assumed to be the same because the assumption for all of this lesson is that this is a regular polygon. Regular meaning that all these side lengths are congruent and all of these internal angles are also congruent. So I'm going to take my 360 degrees and divide that by 7 to find theta. That is my first step. Let's go ahead and write that down. Theta is going to come from taking 360 degrees and divide it by 7. So I'm not going to simplify this with any calculator. I'm going to leave it until the very end. That way we can swap out 7 with 11 or 9 or whatever, however many sides I have. But let's leave it unsimplified for now. So I have theta. The problem is, if I have theta, I don't have any right triangle. This triangle right here has no right angle. If you have no right angle, you cannot use trigonometry. You cannot use Pythagorean theorem. Everything is kind of locked up. So in order to use trigonometry, to use all the tools that we have to first draw an auxiliary line to find a right angle. So the auxiliary line that I'm seeing is drawing a line straight through the center of the triangle, and that gives us a right angle right here. Now that we have a right angle, I need to analyze this right hand, or I could do the left-hand side of this triangle. For this triangle, I notice that this angle up here, we cut theta in half. Let's go ahead and call this new angle right here some other variable such as alpha. To find alpha, alpha is the same thing as theta divided by 2, which is the same thing as taking 360 degrees divided by 7 and dividing that by 2. The problem here is I have fractions nested inside of fractions, and there's a helpful trick that I'm going to leave in the notes. And let's go ahead and write the trick up here. I'm going to call this the fraction trick. If you have a number like 1/3 and I divide it by another number like 5, how do I do this problem? There's a fast shortcut that I'll jump from here to the very final answer in one step, but let me show you the long way first. 1/3 divided by 5 is the same thing as 1/3 divided by 5 over 1. And whenever I have fractions divided by fractions, this is the same thing as 1/3 divided by 5 over 1. Fractions divided by fractions, I use a keep, change, flip rule, and this is going to change it into keep the fraction 1/3, change it to a multiplication problem, and 1/5, and that's going to be multiply the tops is 1, multiply the bottoms is 15. Or I'll just leave that as 3 times 5 so we can see the trick a little bit faster. So my trick is to get from this step, which I'm going to erase the 1 over here, I can get from this step all the way to this step in one shortcut. The way that I do that is whenever I divide by a number, I simply stick it in the denominator of the original fraction. So if I have 1/3 divided by 5, just stick 5 in the denominator and I'm done. So check this out. If I have a fraction divided by a number, all I can do is I can stick this number down here in the denominator and I'm done. So the trick here is this is 360 degrees still in the numerator. The denominator is now 7 times 2. So we have our angle. It's this number. I don't know what number it is, but it is some number. And I also have this length here because this length originally was 9, but I cut it in half. Let me go ahead and relabel that. This original length for this entire base of the triangle was 9, but I cut it in half. So this length right here is 9 divided by 2. I cut it in half. So I have two numbers. I have two numbers, which means I can find anything else about this triangle that I need. The other two things that I can find in this remaining right-hand side of this triangle is the height of my triangle or the hypotenuse of the triangle. This hypotenuse of the triangle is not going to be useful to us because it's not useful for finding the area of a triangle where my formula is base times height divided by 2. Those are the two lengths that I'm trying to identify. I already have the base of 9, this length down here. What I'm missing is the height of the triangle. So let's go ahead and call that height y for now. We can solve for y using trigonometry with our other two lengths and angle. So I'm going to set up a trig function. Just very quickly, let's remind ourselves that opposite of the angle of reference is my opposite side. I'm going to go ahead and label that an O. And this side that is right next to my angle that is not the hypotenuse is known as the adjacent. I'll label that A. So I need to relate a trig function with O and A. That makes the OA sound from TOA in SOHCAHTOA, meaning we are using tangent. Tangent of my angle, in this case my angle is alpha. I'm going to go ahead and rewrite alpha, which is 360 degrees divided by 7 times 2. If I take tangent of that angle, it's going to be equal to the opposite over the adjacent. The opposite is 9 over 2, and my adjacent is y. Again, I could use that trick where I put y down here, but I'm trying to solve for y. Y needs to be by itself. I'm going to use the trick from earlier in this unit where we switch these two diagonals. Again, technically this tangent is up in the top and it's divided by 1. I have my two fractions where I can switch these two diagonals, and my new equation becomes y is equal to 9 halves, all of this divided by tangent of 360 degrees divided by 7 times 2. And now I'm going to use that trick where I have a fraction divided by a single number. I'm going to stick this single number down here in the denominator. So this is now going to be equal to 9 all divided by 2 times tangent of 360 degrees, and I need to write that a little bit smaller, tangent of 360 degrees divided by 7 times 2. So now I have the height. This right here represents the height. I'll write a note to myself that that represents height. So this quantity right here is the height of the triangle. Now that we have the height, we need to find the area of the triangle. Again, to find the area of the triangle, we needed the base times the height, this base times the height, and then divide by 2. We have all of those measurements. We're ready to go. So let's go ahead and write down everything that we have. So for our area of the triangle, area, I can write a little bit neater, area of the triangle is going to be base times height divided by 2. We know that the base is still the base of the entire triangle, not just this half of the triangle, but the entire triangle has a base of 9. So I'm going to go ahead and rewrite 9 for our base, times our height. And I just wrote a note to myself, this is the height. So it's going to be times 9 all over 2 times tangent of 360 degrees divided by 7 times 2. Let me write that a little bit neater. 7 times 2. And then that was base, that was times height, and now I need to divide by 2. And I don't really have enough room to divide by 2 right now. I'm going to use that trick where when I divide by 2, that's essentially putting the 2 in the denominator. I'm going to put the 2 down here. So I'm noticing that this is technically a 9 over 1 being multiplied by this entire quantity. So I can simplify this a little bit and say that this is 9 squared in the numerator, and in the denominator I have 4 times tangent of 360 degrees divided by 2 times 7. All right, I have the area of the triangle. The problem now is I don't want the area of the triangle. I want the area of 7 of these triangles. I have this area. I need to find all of these triangles as well. And you'll remember that since there are 7 triangles, I can simply multiply the area of one of these triangles by 7, and then I'll get my answer. So from here, I can come up here and say, now the area of my septagon. And if you didn't know the word septagon, that's the word for a 7-gon, a polygon with 7 sides. The area of the septagon, I take the area of my triangle, which I can go ahead and copy paste, this area right here, and I multiply that area by 7. So I can say times 7, and I'm done. There's my answer. So the problem is I want to generalize this process. This is great. This is the answer, but I don't want to do all that work for every single problem. That's going to take forever. So now I'm going to switch out some variables. I'm going to do what's known as generalization in math. So maybe I need some room, so I'm going to move this stuff up to the top. So here is a generalization. A generalization just means you swap out everything that you can for variables. So the first thing that I'm going to see is this side length was 9, but that side length can be anything. Like, for example, down here, the side length is 2. So let's call that side length some variable. Let's call it x for now. So we're going to say that x represents our side length. And let's go ahead and do the other thing. This could have been a septagon like it is now. It could have been some sort of pentagon, an octagon. It can be so many different shapes. So to count the number of sides, I'll let n count the number of sides. N is the number of sides. And then I just need to swap out all of this equation up here, which I'm going to go ahead and copy paste and send it down here. So here's our final formula. But in the place of 7, remember, we were dealing with a septagon, meaning 7 is the number of sides. So in this case, our number of sides, I'm going to go ahead and replace this. This is supposed to be equal to 7, and the side length here, that in our equation was equal to 9. So all of the 9s change into an x. All the 7s we're going to change into an n. So our generalization is going to look like this. 7 is going to switch to an n. And then this 9 down here is going to switch to an x. And I'm seeing another 7 down here, which I can switch that one out to an n. And now I have a generalization. Notice that the numbers that never change, this 4, this 2, this 360, and that 10 will always stay there. Those are in red. So there's our final answer for today's lesson. The area is equal to that generalization. And then we can use that generalization over here on the right. And I guess I can simplify that a little bit more here. I can put the n up and top. Here, let me go ahead and erase this. I can say this n, let's move it up here right next to the n. So it's going to be n times x squared. And that's all going to be divided by this denominator of 4 tangent of 360 over 2n. Much, much neater. All right. Let's use this formula now. All right. So in number 1, we have how many sides? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 sides. So in this case, n is going to be 11. N represents the number of sides. This is, I'll say, number of sides. And I need to find the side length. Unfortunately, now the side length is not too clear. The entire perimeter, if I add up all these lengths, it adds to 55. And that's why it's helpful to know this formula down here that I haven't filled in yet. So to find the side length when you're given the perimeter, you take the perimeter and you divide it by the number of sides. So I'm going to say number of sides. And we've been calling that a variable. We'll call that variable n if you would like. So in this case, I have a perimeter that is 55. So in order to find my side length, I'm going to take 55 and I'm going to divide by the number of sides, 11. 55 divided by 11 is 5. So therefore, each of these side lengths is 5, 5, 5, etc., right? If you add them up 11 times, you should add up to 55. Now that we have both of these variables ready to go, we can plug this into our formula. I want to show you how this formula works on a Desmos scientific calculator. It's really, really fancy. So if I go to split view here, on my scientific calculator, let me go ahead and clear all of this and move this to the left. All right, so I'm going to type in this formula. I'm going to type in nx squared, and then all that is going to be divided by 4 tangent of 360 divided by 2n. And then you'll get this warning on the right that says, too many variables, try defining n or x. We will do that. Let's define n. Let's define x. So if we say n is equal to, let's go to our last example. X over here was 9, so I'll type in 9 over here. And x is equal to 7. And you get an answer. So the answer that we got up here, we didn't even simplify it that way. I guess I can simplify that right now. This is, here, let me I like my equal to sign to be on the right side, so I'm going to move all of that over. This is approximately equal to, if I'm rounding to one decimal place like I typically do, this can be 302.9. Yeah, just 0.9, 302.9. So that's kind of cool. I can box that. That was their answer from the first one. Although the whole point of doing the first one wasn't to get this, it was to get this fancy formula. So now that I have the formula, I can just fill it in over here. So if I say, okay, n is 11 and x is 5, I can just say n is now delete 11 and x is 5, and I'm done. So how do you show your work? First, you'll identify what n and x are, which I've already done, and then you're just going to write out your formula as if you're plugging into it. So here's my n, and here's my x squared, all divided by 4 tangent of 360 degrees divided by 2 times, there's my n again. So let's fill in our n. Our n is 11, so I'll say 11 goes here and here. And my x in this case is 5, so I'll put a 5 right here. And when I do that, I can just write down the answer that the calculator is telling me. This calculator is approximating this to be about 234.1, rounding to one decimal place. That's the answer that we're looking for, but the important thing is knowing how to get there. If I could, I would force everyone to go through this process over and over again, but that sounds like a lot of work. So as long as you guys are okay just memorizing the formula, I guess that's okay with me. We'll have to settle for that. We're meeting in the middle. All right, so for this one, again, I'm going to write down the formula. I'm going to say, okay, I need to find n, I need to find x. And in this case, how many sides do I have? Let's count. 1, 2, 3, 4, 5, 6, 7 sides. And each side length is, it's easier now, it already told us, is 2. So I can just fill in my formula. I can say, okay, my formula is going to be n x squared, all divided by 4 times tangent of 360 degrees divided by 2 times n. So n in this case is 7 and 7, and x is going to be 2, and I can type that in here. X is 2, n is 7, and I get my answer. This is going to be approximately 14.5. And it's kind of nice to know, like if you are randomly in the wild, maybe you're doing some sort of construction job and you just have a regular polygon, you're like wondering, well, how much is this for all of that paint? Like I need to paint this. I need to know what the surface area is. And there's the surface area. We know how to find area now. All right, well, that concludes our lesson for 8-5, trigonometry and area. Thanks for watching.